above the median, is that what you said? Or anything else? Let me say something else. No? Okay. Okay, so it's a good situation when 75 is, I'm going to say above average, because median could be average, right? So when would it be a bad situation? Well, yes, but when you're looking at your data, we don't know effort here.
Oh, yeah. Like it's below the average.
Below the average. So it would be a bad idea or bad situation when 75 is below average. So here's the results of a random sample of 20 Chapter 1 tests along with the dot plot and the summary statistics, okay? There it is. So Daffy Duck, he scored 65. This is a review from Friday. What is Daffy's percentile? How do we find that?
Don't you count numbers of the things?
Count the numbers of the things. That's right. Can we be more specific? There is counting of things, yes, but what things?
How many there are in general?
Well, we know there's 20 total. Anyone else want to help her out? Apparently it was a very long weekend and we did some brain dumping along the way. Percentile, remember, it means less than or equal to. So I look for, if the score is 65, I look at how many scores are 65 or below. So how many is that?
3.
There you go. 3 out of 20, if we make that a percent, that means it's 15%, right? So Daffy's in the 15th percentile. Remember, in interpreting world, that means that 15% of the people scored a 65 or less. Now, was he above or below the mean?
Below.
Because what's the mean? 80. So he's below the mean, but by how much? We can do the math, people. 65 minus 80 gives me what?
Oh, 15. Oh, wait, negative 15.
Negative 15, yeah. So he's 15 below the mean. All right. So then if we translate that into how many standard deviations, so we're going to round that standard deviation score to just 10. So we divide it by 10. That would be 1.5, a negative 1.5, right? So we would say Daffy's score is 1.5 standard deviations below average. Does that make sense to everybody? All we did was subtract the mean, divide by standard deviation, right? Okay, so look at Bugs. Bugs scored an 88. So we're assuming this is the 88 right here. So how many points on the in the data are 88 or below? Below. 16. Yeah, I did the same thing this morning, Aiden. I did the whole thing. 16. So 16 out of 20 translates to what percent? Here we go, 80%. So Bugs is in the 80th percentile. Meaning 80% of the students scored an 88 or less, right? Was Bugs below or above or below the mean? Above. By how much? By 8. Okay, and then how many standard deviations? Divide that by 10, and that's 8/10 of a standard deviation, right? Alrighty. Now, what you've just done, without realizing it, is standardize those scores. Alright, and when they standardize them, we call them a z-score. So, a z-score is defined as the number of standard deviations above or below a mean. Alright? So, the formula for calculating a z-score looks like this. It's the value minus the mean divided by the standard deviation. Nothing too difficult there, right? We're adding and dividing, or subtracting and dividing, right? Okay, so Porky Pig, he got a 98 on the test. Let's find his z-score and interpret it. So 98 minus the mean of 80 divided by 10. So 18 gives me 1.8. So interpreting means I've got to put context and meaning behind that number, right? How would you interpret it? I would say Porky's score of 98 is 1.8 standard deviations above the mean. How do I know it's above and not below? Because it's positive, exactly. It's positive. If you're subtracting out a negative, it would be below the mean, right? Logic tells you that, and that's true. Very true. All right, everybody up to speed? Writing feverishly? Are you good? You good, Tubman? I don't want to rush you. Okay, moving on. Now look at this. We have 3 dot plots. It's all the same data, but something's been changed. So let's look at what happened to every data point to change it from dot plot A is the original scores, to B. What happened from A to B? How? Can you be more specific on how did it change? Went from 80 to 0, so what did they do to it?
Oh, the scale changed. Like, it shifted the scale.
Uh-huh.
Like from 65 to 95 to negative 15 to 15.
So what did they do to every value?
Subtracted it by 80.
Subtracted it. So it's the value minus the mean. In this case, it was the test score minus the mean. So the mean was 80. Subtract 80, that makes the center now 0, doesn't it? And if it's negative, that means it's below the mean. So we did the value subtracted 80, or the mean. Now, comparing dot plot A and B, look at the shape. Did the shape change?
No.
So, did the shape, no change on shape. What about the center? Did it? This has a center of 80, this one has a center of 0. That seems different to me. Right? So it's now 0. What about variability in the spread of the dots? Did they change at all? No. So the variability stayed the same. Okay. Now looking from B, dot plot B, dot plot C. Look at those two. What do you notice changed? Divided by 10. What is 10 relative to this data? Standard deviation. So it's not just the value minus the mean, but now we have done one step further and divided by the standard deviation. And that's what we refer to as a z-score. So every data point from B to C we divided by 10. So I'm just going to say standard deviation now. So, did the shape change? No change in shape, none. What about the center? Center didn't change. 0 divided by 10 is still 0, isn't it? So 0 divided by 10 is still 0. So essentially there's no change. Variability. Did the standard deviation change? Looky there. Here it's a 10. Here it's a 1. So maybe a little bit, maybe. So variability, 10 divided by 10 makes it a 1. Yes. So what did it get? It got smaller, right? Definitely smaller. So this is what happens every time you standardize a set of data. You always subtract the mean, that makes the center then a 0, and then divide by standard deviation. So what does it mean? What is the mean and the standard deviation of a distribution of z-scores? Well, the mean is always going to be 0. Because to get there, you have to subtract it from itself, right? The standard deviation is always going to be 1. Is this true for any distribution? Yes. No matter the shape, the center of the z-scores will always be a 0, and the standard deviation will always be a 1. Okay, so if it's right skewed, left skewed, these rules still apply. Doesn't matter. Now, why would we care? Well, because often things that we want to compare are not measured the same ways. For instance, look, Daffy took an algebra test and he made a 96. The class average is 94 with the standard deviation of 3%. Bugs took an AP Calc test and made an 83. The class average was 70 with the standard deviation of 5. Daffy says that he did better, but Bugs disagrees. Who did better relative to their exam? So you see what I'm saying? Two different classes, you can't say they're the same anymore, can you? So let's standardize their scores so we can then compare apples to apples. So Daffy, he got a 96. Minus that average was a 94 divided by 3. So when I subtract, I get 2/3. So he has a z-score 0.67. Then there's Bugs. Okay, he made an 83. Subtract that class average. It's 13 divided by the standard deviation of 5. We get 2 3/5. So that's 2.6. So assuming, I'm just pretending here for a moment, I don't really know if this is true, but if it's a normal shape and 0's in the center, that means Daffy's like right here, because 0.67 is barely 1 standard deviation above, right? And then Bugs is like 2 standard deviations, 2.6. So who actually did better? Bugs, right? Even though his score was lower, relative to the data, he actually did better. Does that make some sense? When we use this in real life, guys, ACT, SAT, all the time is used here, okay? Because they grade them very differently, don't they? Scores are so different. How do you know how you did comparatively? Well, you have to standardize the scores. Do it like this. All right? Now, here we go. Standardized values. See if you remember. What was the formula for a z-score?
Value minus mean over standard deviation.
Nice. Value minus mean over the standard deviation. So when we interpret a z-score, here's another interpretation. We've learned standard deviation, you've learned percentile interpretations. Now we're adding another one. Here's z-scores. So we're going to put in context. Bugs' exam score is 2.6 standard deviations above the mean. Now it could be below here, right? If my z-score happens to be negative, it could be below. Now, do you remember this? All standardized distributions have a mean of what?
0.
Good. And a standard deviation of
1.
mhm. And we use this to compare things from what kind of data sets?
Different.
Different data sets. Okay, now, it's like 2 lessons in one. You're learning what a z-score is, but you're also learning what affects mean, what affects standard deviation as far as changes. So the first thing is, given a distribution, if you add or subtract a value to every single data point, will the shape change? If you don't remember, go back to that middle graph on the back page. They stayed the same, didn't they? These stayed the same. The shape and the variability stayed the same. But the center, the mean, is going to be added or subtracted by whatever that A value is. So if I add $10 to every average cost, that means I add $10 to every single data point. Okay, whatever A is. So that's adding and subtracting. However, it's different when we multiply and divide. This is when we divided by standard deviation. Now, did the shape change?
No.
The shape stayed the same. The center got divided. Remember, 0 divided by 10 was still 0. In this case, it really didn't look like it changed, but it did. Okay, so the center and the variability, the standard deviation, both changed. So we multiply and or divide by whatever B is. Both of them changed, but the shape does not when you're multiplying and dividing. You will see some practice problems on this, so we're going to do one here in a sec, okay? All right. So according to an article in Yahoo News, you should change your sheets every 7 days at minimum. To investigate the sheet changing habits of adults, a random sample of 20 adults reported on how often they change their sheets using an anonymous survey. Here's a dot plot and statistics of the results. So these are days. Some people went 120 days. Yikes. No judgment here if that's you. Okay, so there's the data. So I'm going to give you in your tables a minute to see if you can work through A, B, and C. Doing some conversions. Bren, if you want to join a table, feel free. You are not locked into where you are. Benefits that would arise from changing their sheets more often. So after reading it, they agree to change their sheets 1 week sooner. 1 week sooner would mean I need to subtract a week, right? So we're asking ourselves, okay, does subtraction affect shape?
No.
No. Based on what we've seen, subtraction will not change our shape. So the shape is going to stay the same. Will it change the mean? Yes, so all I have to do is subtract 1 from 6.11 and I get 5.11. But does subtraction change standard deviation? No. It stays the same. Okie dokie. Ring a bell? You're going to see some practice questions in your packet like this where they give you scenarios and you have to decide what is the new mean, what is the new standard deviation based on these changes. And those are the questions you need to ask yourself. Then lastly, it says, now suppose you convert the time before changing sheets from part B to z-scores. So you do all the z-scores from the whole set of data. What would be the new shape, mean, and standard deviation of all the data? Well, the shape's going to stay the same. It never changes. Okay? The mean, however, changes to 0 because we take that center and we subtract it from itself, right? And then we divide it by the standard deviation. 0 divided by anything is still 0. So the standard deviations become a 1 because we're using the standard deviation of the data. Why is that the case? Because that's true of all, it's not standard deviations, it should be distributions. I can read. Standardized distributions, not deviations right here. Sorry about that. Okie doke.